Everyone, welcome to lesson number 2 on unit 3. We're going to talk about solving exponential equations. So right off the bat, there's this little restrictions, right? We're talking about a b value that's bigger than 0, and we don't want to work with 1 because 1's not very interesting. Okay, it can be fractional, it can be whole numbers, right? We just want to make sure that it's positive and not 1. What's going to happen here is if we have some base to the power of x would have to be equal to some base to the power of y if and only if those exponents are equal. So what's really happening here? What it's telling us is that if we can somehow make our bases equal to each other, if we can do that, then we can just set the exponents themselves equal. Okay, and vice versa. If we happen to have two exponents that are equal, those things could only be equal to each other if the bases match. So we can go in both directions. We're going to be trying to make our bases match. Once we get that, we're just going to set each piece equal and solve. That's the direction that we're going to be going for this. Okay, so when you look at some of these examples, right, you'll notice the first example says solve for x. Right now, we have two different bases. Right, we have 2 and 8. I need to, if I can, change these so they're both the same base. Sometimes I can change just one, sometimes I have to change them both. In this situation, what I'm noticing is that 8 is really 2 to the power of 3. Right? 8 is equal to 2 to the power of 3. The reason why I'm doing that is because I already have a base of 2 over here. Right? I have 2 to the x minus 1. Now there's one thing that's somewhat still missing. Right? I said 8 was 2 to the power of 3, but this is 8 squared, so I need to make sure that I put that 2 up there as well. Now that I have both bases matching, right? I have 2x minus 1 on one side, and I have 2 to the power of 6 on the other. Now that my bases match, I can get rid of the bases altogether, and I can just work with their exponents, right? So I have x minus 1 on one side, and I have 6 on the other, because I can ignore my bases at this point. I'm going to solve by adding 1 on both sides, and we come up with x equals 7. Okay, so this whole process is trying to get the same base. So we're going to look at the second problem. I have 16 and I have 4. Now I could change these both to a base of 2. That's always a possibility. But I can also make this a base of 4. Right? Because 16 is really 4 squared. I still have this stuff that I have to put on the outside as well. And this works better because now I have 4s for bases. One thing we've got to be careful of here, we have to make sure we distribute this 2, because this is multiplication here. Right? So what we have is 4 to the power of 2x minus 6. That's equal to 4 to the power of x plus 1. Now that my bases match, I can get rid of those, and I'm going to work with just the exponents. 2x minus 6 equal to x plus 1, and then we'll solve like usual. Right, subtract x. Add 6 to both sides, and we come up with x equals 7. So here's one for you to try out on your own. Pause this video and resume it when you're ready to try checking your answers. Alright, let's check out how you did with this one. As I had mentioned before, sometimes you only have to change one. In this situation, we're going to have to change both bases. Right, because there's no way that I can make an 8 turn into a base of 4 and match here. But I do know that 4 is really 2 squared, and that will be the power of x. And 8, I know, is really 2 to the third. And I'm going to bring that stuff down as well. Okay, so this is going to give me 2 to the power of 2x on one side. We have to distribute on the other side, so we get 2 to the power of 3x minus 15. Now that we have the same base, we can basically get rid of those, and we'll work with the exponents. 2x and 3x minus 15. If I subtract 3x from both sides, we get negative x equals negative 15. We'll divide by negative 1, and we get 15 for our solution. Did you get 15 for your solution? I'm hoping so, because these are pretty easy. There's another situation that we might come up with. Okay, this one, same instructions, right? Solve for x. We're not going to do much different. We still want our bases to match. But what I notice here is that I have a 5 and I have a 1 over 25. Well, that's not really that big of a deal, because I'm still looking at this 25 and I'm thinking, all right, that's really 5 squared, isn't it? Right? 25 is 5 squared. But I have it under 1. And if I remember from some of my other exponent properties, anytime I have a value like that under 1, I can use a negative power, and that'll get me that fraction that we have, right? So instead of it being 5 to the second power, I really want that to be 5 to the negative 2 power. All right, so here we go. We've got 5 to the x minus 3 on one side, and we just said this whole thing is really 5 to the negative 2, right? That's going to be equal there. I'm going to have to distribute this negative 2. Okay, so we still have 5 to the x minus 3 on one side. Now we have 5 to the negative 2x plus 2 on the other. Now our bases match, right? Our 5's match. So we're just going to keep the exponents, and we'll start solving. I'm going to add 2x to both sides. So 3x minus 3 equals 2. We'll add 3 to both sides. And one more step, we'll divide by 3. I hate fractions. Sorry, I hate decimals rather. I love fractions. I'd much rather leave this fractional answer 5 over 3 than you giving me a decimal. Okay, 5 over 3 is much more correct than any decimal would be. Okay, so we now have a problem for you to try out on your own. Right here, pause the video and resume it when you're ready to check your solution. Okay, let's see how you did with this one. What I'm noticing myself is that 1 over 27 is really 3 to the third power, and to get it under that 1, we're going to have negative 3. Right, so hopefully you chose this for your first step. 3 to the negative 3 to the x plus 2 power equals 3 to the 4x minus 1 power. We're going to distribute. So we have 3 to the negative 3x minus 6 equals 3 to 4x minus 1. At this point, our bases match. We just work with the exponents. Let's add 3x to both sides. So negative 6 equals 7x minus 1. I'll add 1. Negative 5 equals 7x. We'll divide by 7. So our final solution is negative 5 over 7. Hopefully you got that solution as well, and you didn't change it into decimals, because I'm not a big fan of decimals. Alright, we're going to move on to something a little bit more practical, having to do with exponential equations. Okay, and it's going to be something called compound interest. This is something that you can really get into with economics and banking and that type of stuff, and you can do some pretty basic problems having to do with interest rates and bank accounts and CDs and that type of stuff. Okay, do these get more complex? Absolutely. Are we going to look at another more complex one later on in this unit? Yes. But for right now, let's just work with some of the basics, right? Compound interest. So here's a very basic formula right here. We have A equals P times 1 plus R over N to the N times T power. This A is just going to be the amount after so much time. Right? It's kind of like our function, our y value, our result. We got to decide what each of these values stand for. Okay, in this situation, P is going to be our principal. It's just your starting amount. Okay, if you invest $100 one day into a banking account, that would be your principal, would be how much you invested, 100 bucks. Okay, R is going to be your interest rate. Normally they mention interest in percentages. As you can see in the example down here, it's showing a percentage. We're going to want to change that to a number. So we're going to have to move the decimal twice to the left and fill in any zero placeholders. Okay, so that's something we got to remember with interest. N is going to be the number of payments per year. Now, the deal with this is that they're not going to always tell you the exact number, right? They might tell you bi-monthly, right? Bi-monthly. They might say quarterly. They might say 3 times per month, for example. So you might have to calculate what each of those are. So just keep in mind, there's 12 months in the year. So if they say something like, every 4 months, well, then that would be 3 payments in the year. If they say 5 payments per month for some reason, then you'd be doing 5 times 12. So just be aware of this N value. You have to calculate it most likely. Our last one would be T, which is the number of years. They'll usually tell you how many years something is being invested for, especially something like a CD. If you ever invest in a CD at a bank, they'll tell you, this is a 3-year CD. You won't be able to touch it for 3 years. Okay, so they're usually very upfront with how much time. So we need this formula, and I'm going to leave it up here for this first problem. And when we go through the problem, we'll read it first, and then we'll go back and we'll start labeling which things are which. All right, so here's what our example looks like. A bank account has an interest rate of 3.8% compounded bi-monthly. If you initially invest $6,000, how much will be in the account in 8 years? All right, let's go back and think about some of the things we need. All right, we need principal, which would be the starting amount. So they tell us that if we initially invest, initially means starting. So 6,000, that's going to be our principal. The rest of the formula, it says 1 plus. Then we need R, our interest rate. It actually says interest rate, but again, we don't want that percentage. So we're going to need to move this decimal point over 2 places, and I need some 0 placeholders. So our R value here is 0.038. That's also going to go into the formula. N, number of payments per year. This says bi-monthly. Bi means 2, so every 2 months. So if there's 12 months in a year and we're doing it every 2 months, that would be 6 times per year. So N equals 6. So I'm going to put a 6 down here. I also need one up here in my formula as well. So I've got 6 times. And we need a t value, right? Because it says times t. So they tell us down here in this problem how much will be in the account in 8 years. 8 years would be our t value. So we're doing times 8. I'm just going to clean this up a little bit. That right here. All right, we got 6,000 times 1 plus 0.038 over 6. 6 times 8, that's going to give us to a power of 48. Now, this right here, if you can, in a calculator, get it into one number that's not a repeating decimal, it might be easier to type in that way. However, you're probably going to be able to just type this straight in how it is here. If you're using one of the school calculators, which is a TI 83 or 84, right, you're going to need parentheses around this piece right here, right? So you'll have double parentheses. If you're working with Google Calculator, you might have to do the same thing. Or if you downloaded Desmos already, the calculator program I suggest on your phones, you can type that right in. Right? I've already calculated that, and what I'm coming up with is 8,123.82. Okay. So again, getting this, not really difficult, right? You go through, you label each piece, plug them in. Just make sure that you type this into the calculator or whatever calculating function you're using. If it's an app on your phone or whatever, just be careful with this. This is what we were hoping to get. So I've got one more problem for you to try. Okay, write down the problem, label each of the pieces as you normally would, pause this video, and resume when you're ready to check your solution. Alright, let's check out how you did with this. I'm going to read it through and label as we go along. Right, a bank account has an interest rate of 2.15% compounded monthly. So our rate is going to be 0.0215 compounded monthly. There's 12 months in a year. So N is going to be 12 for us. If you invest $550, that's our principal or starting amount, how much will be in the account after 15 years? Time here is 15 years. So our formula, amount equals, our principal was 550 times 1 plus, our rate was 0.0215 over n, which we said was 12, to the 12 times 15 power. Cleaning that up a little bit, we got a equals 550 times 1 plus 0.215 over 12 to the 180 power. That's what I'm going to type into my calculator on Desmos. So let me type that in real quick. And the gremlins on the inside are calculating. They're coming up with 759.097. Now, there is no thousandth of a cent in the United States, at least with banks and coins, as far as the public is concerned, so we got to round that up. That 7 is going to tell that 9 to move up to the next number, so a 10. So our amount, what we get out after 15 years would be $759.10. That's compounded interest, and that's the end of our lesson on exponential equations. If you have any questions, leave them in the comments or bring them with you to class. I'd love to answer them there. Until then, see you next time.